Let's finalize this section with the bode plot. Note this is the video 22 up to this point, and video 23 then gives some information about the bode plot with some interesting application information. For the bode plot, I use the following fact. A PDT1 block with KD and TD and T1 is nothing else than the series connection. Can be understood as a series connection of a pure PD. This is a PDT1 in series connection with a simple PT1. Now, if you look for the transfer function of a PDT1, this is a product. Where is it? Here you can see the product of the numerator function. This is a PD multiplied with 1 divided by 1 plus PT1. That is a simple PT1 just with a K1 and a time constant T1. And here this gets a K and this gets a TD. So with this knowledge we can easily draw the bode plot, because this bode plot is known. It is PT1. The transfer functions has to be multiplied of both sections, and the bode plot has to be added. So we have to look how is a bode plot of a PD, and here we know if we multiply the functions we have to add the bode plots. A big advantage of the doubled logarithmic case, we have just simply adding two curves, and this is graphically easily done. The only thing is you have to look for the bode plot of a PD and the PDT1 we get by simply adding the PT1 case. Okay, the functions, the complex transfer functions can easily be written. F of omega, the complex function, is K 1 plus J omega TD, is the part of the PD multiplied with 1 divided by 1 plus J omega T1. Yeah, this is a PT1 part and this is a PD part. The phase is also easily written. That is the arctangent of this part is arctangent real imaginary part of this part divided by real part. So this is just arctangent omega TD minus arctangent the phase of the PT1. Now, parentheses means this is of course the argument of the arctangent function. So the magnitude of our complex frequency response is easily written is K times square root 1 plus omega TD squared multiplied with 1 divided by square root 1 plus omega T1 squared. This is already done, and here this is very similar to a PT1, but some properties are inversed. Let's start with a bode plot. F magnitude in dB of the PD block. That is the logarithmic factor of omega. Now just draw this one. We could do this in different colors. So this should be a black line. Then we know this will be at a red line, a PT1, and in total we can say the addition of both functions then is a green. Yeah, green is bad. Blue. I want to do this in blue. Sorry, I want to do this in blue. Because green is reserved for PD. Or better, I should do this in green. Ah, that is better. I do this in green. Yeah. Green color for PD. Then this fits to my color in the top region. Red is PT1. And then we can add this together in blue. Oh nee, das ist nicht gut. This color is not good. Blue is here. This is then the PDT1. Okay, so start with PD. I want to have, we can only add this if we have something, information about the ratio of TD and T1. I want to draw this in the case that we have here a value 1 over TD, and here should be a value 1 over T1. Then I start drawing this magnitude curve. If omega TD is very small, we have simply the distance k to the 0 dB line. This is constant value, and then of course if I reach the corner frequency of the PD, then the asymptotical curve is different to the correct curve. In the case that omega TD is larger than 1, we have the magnitude function k times omega times TD. And this, we already know, this is an increase with plus 20 dB over a decade. Why should I not draw this curve in green? I don't know, so please wipe this. Sorry for this. The axis could of course be black and the curve should be green. So the corner frequency is 1 over TD because at omega is 1 over TD. Both asymptotical curves crosses each other, so the green curve goes up here with positive 20 dB over decade, and the asymptotical curves have a cross point, a corner here at 1 over TD, very similar to the PT1 case, and then the exact curve is this. And again, if we analyze the situation at corner frequency, here we have a plus 3 dB difference between asymptotical curve and correct curve. This is the situation of the PD magnitude curve. Now I add the red case, PT1. K is 1, means 0 dB. So for low frequencies, the PT1 has no contribution. And here you can see, okay, if I reach the corner frequency of the PT1, this is not anymore true, but I can draw now the asymptotical curve for high frequencies of the PT1 with negative 20 dB over decade gradient. And if I draw the exact curve, this should look like this. You know, this difference between the exact curve and the cross point of the asymptotical curves is again 3 dB. So this is the PT1. Green is PD. And now we can draw with blue I think I should select a little bit darker blue, a little bit thicker. We can now add both curves, the green and the red curve added gives, for low frequencies, the PT1 has 0 dB, so the blue is equal to the green curve. Now this is true for low frequencies, and here you see, starting here in the middle, then we will have more and more difference to the green curve. And starting with this corner frequency, we can say, starting with this point, the positive 20 dB over decade increase is compensated with a negative 20 dB over decade decrease at the PT1. So the asymptotical curve is then a horizontal line. So what we can say is, here we have 3 dB deviation. Final value is this, and you see here the curve looks like this is S form, starting with K here in dB, of course, K in dB. Then we have an increase up to the final value here, and what we can give as a further information in this situation, the gain increase from K to this. What is this? The gain increase. Yeah, we can say, okay, the gain for large frequencies, F for omega very large. Very large means very right from 1 over T1. Magnitude is how large is. Okay, we can here neglect this one and here neglect this one, because these expressions are very, very large. So we can write a K times, what is this? If one is neglected, this is square root of omega Td squared. This gives omega Td. So we have an omega Td here. And then this square root of the PT1 with neglected one here is omega T1. Omega T1. Here we can erase the omega factor, and we have as a result, this is K times step depth. So if this is K, again in dB, and this is K times step depth in dB, we know in logarithmic diagram this piece is the step depth in dB. And that is the reason why we call this parameter step depth. That is the depth of this step in the bode plot. Yeah? Could also say that not the depth, but the height of the step, but step depth is the common name spread in the literature. So we can say, okay, the high frequency gain increase is defined by this step depth value of the PDT1. So far, we can then have a quick look on the phase curve. The phase curve is again the phase of the PDT1 plus the phase of the PT1. This can be drawn as the following diagram. Again, logarithmic value of omega. Here we have a positive 90. Here we have the negative 90 degree mark. We make also now a 3-colored curve. Let's start with the well-known PT1 phase in red. Now we have an arctangent function which crosses the middle value here, the negative 45 value at this frequency. So we have an arctangent curve looking like this, ending with minus 90. And we have a similar case in our blue situation, our PD situation. This is an arctangent function with positive sign, so we go up to plus 90, starting with 0. And then the curve goes up through this middle value. Again, this is plus 45 degrees, ending up with positive 90 degrees. So, and you see, what happens very quickly if we add both phases for the PDT1 in blue. We see the 0 plus 0 gives 0, plus 90 minus 90 gives 0. So for high frequencies we end up in 0, and then here we go up with a green curve, but here starts the negative value of the PT1, so this will be a little bit deeper than green. Yeah, and we can say the phase curves have the same shape, and if we add this green with the red curve, we can prove mathematically that directly in the middle between these corner frequencies we have a maximum, and we get a symmetrical curve which goes up here and here goes down with a maximum value at which frequency. I will show you first the phi max value in the table, and I will tell you something about the middle frequency of the phase curve. In black I give you some values where we can see, okay, this is this is phi max. No, sorry. First, the question is on which parameters phi max depends on. Yeah, phi max is a phase maximum. The phase expression is, where is the phase expression? Sorry, wrong place. Here, you see the phase expression carries only omega, Td, and T1, not K. So phi max cannot be a function of K. Can only be a function of Td and T1. If you look here in this curve and say, okay, phi max is a maximum between these both frequencies, then you can say, okay, if the distance of these frequencies is larger, so this goes to the left, this point goes to the right, then of course we go up higher. If the distance goes down, the decrease comes earlier and the maximum is smaller. So we can say the phi max depends on the distance of these both frequencies. In logarithmic scaling means the distance, this is a ratio, and the ratio of the time constants is the step depth. So we can find out the phi max value depends just only on the step depth. If the step depth is 1, phi max is 0, there is constant phase 0. If that could be calculated with mathematical methods. I don't want to show you really the method to show you how to calculate the values. That could be done with numerical calculation methods. I give you the result. If we have a distance of 1 octave, then the phi max value is 19.5 degrees. If we have 2 octaves, we have 36.9 degrees. If we have a decade distance, we have 54.9 degrees. If there is a very big distance, we have a maximum of 90 degrees. More is not possible. That is just the PD block if the T1 is infinity. The question is, where is this frequency? This is in the middle between both frequencies. This is the average value of this point and that point. Average means sum of both divided by 2. If these are logarithmic values, then the sum of the logarithmic values is a product of the frequencies. And if I divide a logarithmic value by 2, then this is a square root function. We can say, okay, the omega max value of the phase curve, the middle point between this is 1 divided by the square root of T1. The geometrical average of these both frequencies. Yeah? The geometrical average means the product and then applied the square root function that is a geometrical average value. There you can find the omega max value. Okay, yeah, applications, and then PD and PDT1 are discussed in enough details. Application. I want to show you one simple control system. This control system is standing in the Technische Hochschule. I'm working at home, so at this time I have this application not in my hand, so I cannot show you with a video, but I will do this later in another video as an example for application. If I have a magnetic ball hanging in a magnetic field in this way, and I want to control the distance, this distance here. If I want to hang this ball into this magnetic field, I need a controller, and we have a hardware which can do this in school, and I can show you this. And the hardware contains a controller which is a PDT1 controller. Yeah, this system can be stabilized with a PDT1. Can be controlled with PDT1. So a PDT1 could be a good controller. Another application is second application. This filter can be used as for noise reduction in signal transmission. Other name then, of course, the signal system engineers called this with the other name. They don't know what a PDT1 is. That is the real control system name. Other name is de-emphasis, pre-emphasis, de-emphasis, de-emphasis, pre-emphasis. This is a method for noise reduction. Used in UKW audio transmission in Europe, or in music players with record players in record player. The idea is very simple. I just want to show you this idea very quickly, because this is not so important for control systems, but I think it's a good link to other knowledges. If I have a signal generator, audio signal for example, then I send this through a PDT1 with steps larger one, then with the sender and the receiver. In the receiver or in the record player, I have a PDT1 with steps smaller one, same value but the inverse value, and then I have my signal, say U2 of t. So normally in signal transmission we have a noise added to our signals with which we send our music or so. The trick is now, here you add the amplitude 0 dB, you add the amplitude of high frequencies. Now that is the F magnitude of this filter. That means high frequency signal parts have larger amplitudes. This is possible because in audio signals the low frequency amplitudes are much larger than the high frequency amplitude. So this increase leads not to a saturation. Then you send it, and in the receiver you then should have the opposite curve, and here with the same corner frequencies, yeah, it should be omega 1, omega 2, omega 1. This must be the congruent filter function, otherwise this doesn't work. Here you have the same decrease of amplitude. That means all noise which is added here is suppressed exactly with the step depth value. So if the step depth is 20 dB, this is a factor of 10, then the amplitude increase here is a factor of 10, here the decrease is a factor of 10, then the noise in this region is damped with 20 dB, and this is minus 20 dB, and this is just very effective in noise reduction. But of course you need this filter, and in the record players, of course, you have included this filter. It's I think the third time constant is available in this type of record player hardware. That's another name, and in my first project you will see the PDT1 then gives us information about the power of the motor. That's the third application. Comes the next step. Before we start the first project, I should give you some information about the PI controller. This comes with the next video. This is a video with the number. I have to look in my list. Video with the number 23. Video 23.